Okay, so in this video we're going to be looking at the second type of stereoisomerism, optical isomerism. And we're going to have a look at what makes an optical isomer, and we're going to draw some examples. Okay, so optical isomerism occurs when we have an asymmetric molecule. In other words, it does not have a plane of symmetry. This means that there will be two forms of the molecule that are mirror images of each other. They'll appear identical in every respect except that you can't superimpose one on the top of another, just like your left and your right hand are not superimposable. Optical isomers, therefore, are molecules which are isomers which are non-superimposable mirror images of each other. Now that's an absolutely key definition. Okay, so you have to make sure that you've got that definition correct. Non-superimposable mirror images. One way to identify an optical isomer is to find a carbon with 4 different groups attached to it. We call this a chiral carbon. Now you need to be very careful. Optical isomers are non-superimposable images. There are ways you can get a non-superimposable mirror image without having 4 different groups around the carbon. So students quite often muddle these two things up. Chiral carbons are important, and if you have a chiral carbon, it will have optical isomers, but it's not the definition of an optical isomer. So please make sure you've got that definition correct. So we're looking at this molecule, 2-chlorobutane. This is the carbon that I'm interested in, because it has 4 different groups around it. And this is my special carbon. This is a chiral carbon. Okay, so basically I had to get creative and try and do this using what I had around the house. So apologies, but this is my best attempt at making a optical isomer. So here I have one version of my optical isomer, and you can see that I've got my 4 different groups, and on my other molecule I have its mirror image. So if you imagine there is a line down my piece of paper here, okay, and this is a mirror image of this one. Okay, so now what I have to do is I have to look at superimposing one on top of the other. So if I line up my red jelly babies and these things, okay, you should see that my green and my orange don't match. Okay, so however I rotate this, and I have to rotate it quite carefully because it has a tendency to fall apart. However I rotate it, in whichever orientation I've got it in, it won't stack one on top of the other. So whatever happens, it's non-superimposable. Basically, superimposable means I can't stack one on top of the other. The other way to look at that is to think about it in terms of hands. So if I have one hand, I can't superimpose the other hand on the top. So the thumbs end up in the wrong places. So whatever I do, I can't superimpose that hand on top of that one because the thumbs are in the wrong place. Okay, no matter what I do, it's not going to fit. It's a bit like trying to fit a left hand into a right-handed glove. It doesn't fit. So we can draw these optical isomers using normal 3D convention. So I'm going to have my chiral carbon, I have a hydrogen, I have a chlorine, and then I have my 2 R groups. So I've got a CH3 group there, and I've got a C2H5 group. Then I've got my mirror. This is dotted line representing my mirror. And then I've got the mirror image on the other side. So you've got to imagine there's a mirror between these 2 molecules. Right, that should be hashed C2H5. So this is my chiral carbon. This is the carbon we were talking about that has the 4 different groups around it, and they are non-superimposable mirror images. Okay. Now another example would be 3-methyl hexane. If I draw 3-methyl hexane out just normally, So I've got 1, 2, 3. I've got a CH3 group here and an H. And I've got lots of H's. I'm not going to draw them all in for you. You can do that yourself. And this is the carbon I'm interested in because that's my chiral carbon. It has a C2H5 group. It has a C3H7 group. It has a CH3 and an H. So again, if I draw the 3D representation, I have a carbon which has a hydrogen on it. I have a C3H7 group. I have a CH3 group, and going behind I have a C2H5 group. Okay, and then I have again my dotted line to represent my mirror, and I have a carbon, I have a hydrogen, and again I'm just going to draw the mirror image. So I have a C3H7, I have a CH3, and I have a C2H5. So those are again our optical isomers. So what I'd like you to do now is to pause the video and have a go at the table on the next page. Okay, so the first molecule that we're looking at on this page is propan-2-ol. Well, as you can see here, it's got 2 CH3 groups, so it's not got those 4 different groups. Its mirror images, we would say, would be superimposable, so there are no isomers present. So that does not have optical isomers. If we move down now and have a look at the next one, 3-methylhexane. We've already had a look at this one, and we do have this chiral carbon here. So we would expect there to be, and there are, 2 optical isomers, where one is a mirror image of the other. Okay, notice the wedges, the dotted lines, and the 2 straight lines indicating a 3-dimensional arrangement. Next one we're looking at is 1-chlorobutane. Again, you've got 2 hydrogens, so there's no chiral carbon. If there's no chiral carbon, then we say that the mirror images are superimposable. So again, I don't have any optical isomers. The next one we're going to look at is butan-2-ol. And here I've got this carbon here, which has 1, 2, 3, 4 different groups on it. So it does have a chiral carbon, therefore it does have non-superimposable mirror images, and I can again draw the 2 3D arrangements of them there. Okay, so I've got my carbon, this is my chiral carbon, with a CH3 coming off a hydrogen, an OH group, and a C2H3 group, and its mirror images drawn for you there. Next one on our list is butanone. Again, there's no chiral carbon. There's no carbon which has 4 different groups on it. This sometimes confuses students, but this means it's got 3 groups around it, which would give it a planar shape. And because it's a planar shape, it's always going to be superimposable. So there's no optical isomers there. Next one is 2-methyl-butanoic acid. And again, on this second carbon here, I have 4 different groups. I have a CH3 and H, a COOH group, and this C2H5 group. So again, I'm going to get these non-superimposable mirror images. And the last one on here was 1-chloro-3-methylpentane. Again, very similar idea. I've got 1, 2, 3, 4 different groups. So I've got my chiral carbon. If I've got a chiral carbon, I will have optical isomers, and I can draw them the same as normal. Okay, so that finishes this video for today. So we've looked at the beginning of optical isomers, and we've practiced drawing a few of them and checking to see whether we understand whether or not they are actually optical isomers or not. In the next video, we're going to be looking at distinguishing between optical isomers and some of their important biochemical roles. But that's all for now, and I'll speak to you soon. Take care. Bye-bye.